the title of Advanced Data Structures. So you can see in this module, we will focus on advanced data structures. I will give you two topics. Okay. Part A, Part B, Heapsort. Part C, Part D, hashing. These two, a little more advanced data structures. Part A, Heapsort, Part 1. 2 parts, we complete Heapsort. So you can see we will learn a new sorting algorithm, Heapsort. 8.1, Introduction to Heapsort. So why we need to learn a new sorting algorithm, right? So we have learned quite a lot, right? Yeah. So here I do not count it. So why we need to learn another new sorting algorithm? There must be some reason. So let us revisit sort problem another time. Look at the title here, Sorting with Special Requirements. This time, it's not for the general sorting. We want to consider some special requirements. In the real world applications, you may have the situations, sometimes you have many special requirements you need to consider. So when you consider those special requirements, then the best sorting algorithm could be different. So let's look at what kind of special requirements we need to consider here. All right. The first special requirement, the worst case efficiency in big theta of n log n. So that means we want to make sure the worst case efficiency is not very bad, or we want to avoid very poor worst case efficiency. Because if we recall, all the sorting algorithm we have learned so far, for the worst case, most of them are in this category, right? N squared, big theta of n squared. Most of them. Only one of them not in that category. Can you tell me which one, the worst case, not in this category? One. Correct. Merge sort. Remember, we split right in the middle. That means the data distribution is very balanced. The balanced data distribution will result in good worst case efficiency. So that's the reason we avoid very poor worst case efficiency. Merge, the only one. Okay. N log n, merge sort. Right? So if we enforce this first requirement, only the merge sort can pass this step 1. Okay? But we have more and more requirements. Right? Yeah. Okay. In place. I hope you remember in place. The in place algorithm. Here we're talking about elements. Remember there are two meanings, right? In place algorithm and the in place elements in an array. Two different meanings. In place algorithm. Here we're talking about in place algorithm. extra storage space. Extra storage space. Extra storage space. In this category, big theta of 1, bounded by some constant number. Okay? Bounded by certain constant number. That's the meaning of in-place algorithms. So for our new sorting algorithm, we want it in place. In place, it can save a lot of memory, right? A lot of memory space. If it's not placed, we use a lot of memory space. That's another useful feature, useful property. Can merge sort pass this one? Can merge sort pass this one? No. Merge sort, remember, when we merge two subarrays, we have to use auxiliary arrays. If we do not use extra auxiliary arrays, we cannot merge two sorting arrays. The extra space for the auxiliary array is not bounded by big theta of 1, big theta of k. All right. That's the merge sort. Merge sort cannot pass the second requirement. But at this point, because here we are talking about in-place algorithm, I may like to go a little deeper in this in-place algorithm. How deeper? Let me use quicksort as an example. So let's think about if the quicksort is in place. We have to go a little deeper here. If we look at the partition step, I hope you still remember the partition step. Okay? The general details. The picture. I hope you can still recall the picture we ran the example last time. Quicksort. The partition step is in place, right? Remember, we only need extra space 1, 2, 3, but only for the partition step in place. If we look at the whole algorithm, in place or not, then we cannot say the whole algorithm in place. Why? Let me explain. For the whole algorithm, quicksort. Whole algorithm. We use recursion, right? Can we implement quicksort without recursion? We cannot, right? But when you use recursion, how much memory do you use? Recursion. Your stack could be very deep, right? Because your recursion is implemented in stack. How much memory space you use in the deep stack, relatively deep stack? Definitely, it's not bounded by constant. It's not bounded by constant, right? So you push a lot of data, a lot of intermediate steps into that stack. The stack could be very deep. So here you can see if an algorithm has to be implemented by recursion, then we cannot call it in place. We cannot. So in other words, if you want to get an input, we have to find an iterative implementation. Iterative, we do not use stack. Iterative. So here, this sorting algorithm, we do not use recursion. We will use iteration, for loop, iterative. For loop. Okay? Now, using for loop. So here you can see the drawback of recursion. Drawback of recursion. Sometimes we want to avoid it. Here in this example, we want to avoid the recursion. Okay? Yeah. Third requirement, maintain dynamic data efficiently. Another special requirement, so what do you mean dynamic data? Maintain dynamic data efficiently. Another nice property we want to have. We know data comes and goes frequently, right? During our application lifetime, we maintain some application. During the lifetime, data comes in and goes away frequently. So the data is dynamic. Okay? When you insert new data, then you need to arrange it, right? You need to add it into the array and, organize it in a nice way. But to organize it in a desired way, how much time do you need? Do you need a lot of time to, to put it in a desired place? So here I do not want to say to make it a sorted. Because sometimes we may not want to make it sorted. So I just say put it in the desired place. If that operation is very slow, then very slow, not efficient, it's not good. It's not good. So let's try to understand the third requirement with more details. Because what do you mean efficient? In what category? What asymptotic notation you will feel it's good enough? So we want to see that answer first. All right. So let's try to understand this question first. All right. Now here, so I wrote something here. Yeah. So here, this word, I wrote exertion. Exertion. Because when you have a new data inserted, you need to consider, because you need to do some insertion operation, right? You need to do some insertion operation. The question is, can you do the insertion in an efficient way? That's important. Insertion, if it's just like what we did in the insertion sort. Insertion sort. Remember, insertion sort. In insertion sort, we need a big theta of k, right? This many comparisons. Then we feel not good enough. We feel if we need to spend this much cost to get a new element inserted in some desired location, then big theta of n or big theta of k, because our data size keeps growing, then we won't feel efficient. And which one we will feel efficient? If we can get a log n from n to log n, then we will feel good enough. Log n, remember that corresponds to the binary search. This is the efficiency function, growth function for the binary search. That is for the linear search. Okay? This one is for the linear search. Okay? So in other words, if we get efficiency number similar to linear search, we're not satisfied. If we can get efficiency number close to the binary search, then we will be very happy. You know, binary search very fast. So we are very satisfied. Binary search efficiency. That's the idea. Okay? Because nobody can complain about the binary search, right? People can complain about the linear search, but nobody would complain on the efficiency of binary search. So you will see a huge difference between linear search and binary search. Let me give you, because here we compare linear search and binary search. Let me try to impress you on the huge difference between linear search and binary search. Okay. Try to impress you. Why the difference is so big between linear search and binary search. I just use one simple example. Here I use n equals 2 to the k, power of 2. But here I select a simple one. So n equals 1024. You know that's 2 to the 10th, right? 2 to the 10th. Okay. If you apply the linear search on an array with n elements using the linear search, how many comparisons? Linear. Linear. Let's just use the worst case. Okay? Worst case. This many comparisons, right? 1024. For the binary search, how many comparisons? Approximately, you can see 10, right? Can you tell me if I want the exact number for the worst case? Can you tell me 10 or 11? Exact number. Exact number. 10 or 11. To see that, if it's hard to see that, can you use a simple example, 2 squared? Suppose we have 2 square elements. If I ask you binary search, 2 squared, that's 4. 4 elements if you apply binary search. For the worst case, how many comparisons do you need to do? Worst case, binary search, 4 elements. Worst case, how many comparisons? 2 or 3. 2 or 3. 2 numbers. One is 2, just the same number as the exponent. Another exponent number plus 1. All right. If we draw a binary tree with 4-element array, it's like this, right? Yeah. Worst case, first comparison, second comparison, third comparison. How about that? 1, 2, 3. Okay? Yeah. So here you can see if the n number is power of 2, then the worst case for the binary search, k plus 1. Here, 11. Worst case. If I ask you exact, if I ask you approximate, you tell me 10 is fine. Only one difference. Not too bad, one difference. Okay? But you need to know that is not exact. That is approximate. Okay? Approximate. Here I just recall a little bit. Because I remember I asked you the same question for n equals 32 before, right? If you remember. 32 before. 32, 2 to the 5th. The exact number is 6, not 5. 6, not 5. If the exact formula, you can remember the exact formula, log of base 2, n plus 1. That's the exact formula for the worst case. N plus 1, the seeding function. So power of 2 plus 1, seeding, we need to increase that exponent number by 1. Anyway, so here I just review a little bit. Old knowledge, review. Okay. All right, now, huge difference. Linear search, 1024, binary search, 11. How big is the difference? Right? So that's why I say, for the binary search, nobody should complain. The efficiency of binary search, right? So good. Good. Yeah. But people always complain on the linear search. Okay. Too slow. All right, so let's continue. Idea. We need a new data structure. So here you can see, to develop a new sorting algorithm satisfying all above 3 requirements, it's not easy. Okay? It's quite challenging. When we solve a challenging problem, many times we need to seek help from some advanced data structure. The title of this module, number 5, advanced data structures. So here, we need to construct a new data structure first. So here you can see the importance of the data structure. Because at this point, we haven't considered an advanced data structure, right? After we learn these 4 modules, we haven't considered the data structure. Basically, we just use arrays, right? Other than arrays, what other data structures do we use? No other data structure we use. But here we need to, because sooner or later we will feel the array data structure is not good enough. Too simple. It cannot handle more complex algorithm. So we need to go one level higher in the data structure design. This module we will see. All right. How advanced it is here, we want some binary tree structure in this new data structure. Binary tree. So why binary tree structure? Remember, because here our goal, we want to get a binary search type efficiency. So your structure, your data structure should match the binary search goal, right? Yeah. You should have some support for your goal. Okay? Yeah. So the support, what is the support? some binary tree structure built in inside our new data structure. That is our first step consideration. But how, that's another question. How to make it work, make it happen? We will get it. Design our data structure. Make it as simple as possible. Now we have a lot of freedom to design data structure. Okay? But when you have choices, you want to choose relatively simple options, right? Yeah. Here, let's look at the candidates. Candidates that we can choose from, all right, for this new data structure. All right. Here, basically, we only want to look up in our experience, right? In your experience. You have learned data structures before, right? What kind of basic data structures you have learned before? Can you say something here? Just this. From your 2250 class, because that's about data structure, right? 2250, have you learned some words, names for the basic data structures? Other than array, definitely this array. No. Everybody knows. Just name one more to me. Just one. Anyone. Stack. Good. Yeah, stack. Stack. Number 2. Another one. Queue. Good. Number 3. Another one. Yes. Linked list, right? List. Linked list. Linked list. Let's put linked list here. Because stack and queue, you know, may not be good here. Yeah. So let's put a linked list. I hope you still remember a little bit about linked list. Okay? I know most of you don't like it, right? I do not like it. Okay? I do not like linked list. Okay? All right. Yeah, but here definitely arrays, simple one, right? So if we have freedom to choose, we want to choose array, not linked list. Okay? Yeah. Simpler for the question. Can we use array directly? So if you want to use array, then you need to do some more work. If you use array directly, how can you build a binary tree inside an array? Because we need a binary tree structure in this data structure. But we couldn't find a binary tree inside an array. Okay? It looks reasonable for the linked list because linked list in a binary tree, remember in a binary tree, how do you address the parent-child relationship in nodes, among nodes, right? Linked list, at least, gives you a way to address the relationship, right? Through those pointers. But that could be very complicated. Left child, right child, parent node. You need 3 pointers. One pointer points to parent node. One pointer points to left child. Another pointer points to the right child. How complicated it is. Okay? Nobody likes that way. Although we can do that. If you like, we can do that. But too complicated. We want to avoid it. We want to avoid pointers, right? Pointers. Yeah. Because Java eliminates pointers. In Java, you cannot find pointers. Okay? Yeah. All right. Yeah. So here, next step, we need to figure out the binary tree structure inside array, ordinary array that can help us maintain dynamic data. Maintain dynamic data because when we move data in this binary tree, up and down, binary tree, there are n elements. The height is log of n. Log n. The height of the tree, log n. Then, from top to bottom, we only need to go log n steps. So that corresponds to big theta of log n. How about that? That's what we need. Log of n. That efficiency. But the question is, how to make it happen? So our next. So directly we cannot, but we need to do a lot of work to make it happen. If you do nothing, definitely you cannot make it, right? If you do nothing, you just grab an array, there is no binary tree inside. When you move elements, you cannot get a log n efficiency. So our first important thing to do, build binary tree inside the array. Okay? Yeah. So build a binary tree in an array. First, in our data structure design, we need to do this. Okay? How to modify the array? So you have to add some extra information in your array. How do you address parent-child relationship? If you can find a simple way to address the parent-child relationship, then you're almost there. Without using pointer, we're almost there. So we need a smart but simple, very simple. Not very complicated. We don't like very complicated for parent-child relationship. Here, there is a very smart idea. Okay? All right. Data stored in an array. So here still, I use a simple diagram to explain the efficiency question. Actually, I hope after we use the binary tree as in, in our previous slide, so you can get that point, efficiency. So here, yeah, initially we can sort an array at the beginning, but the question is, when new data comes in, the data is not in order, right? But if you want to make it in order as fast as possible, if you want to find the right location to insert new data, then the linear search way is not good, right? Big theta of n, that's the linear search way. Too slow. So our goal, our target, we want to have a binary search of, efficiency. Now, big theta of log n. All right. So here for the insertion, when we do insertion, remember there are two different ways we can do. The first one, linear search-based insertion. In our standard insertion sort, we use this way, linear search-based insertion. But there is a binary search-based insertion. So we can find the location of the new element faster using binary search-based insertion. That is our design goal here. Design goal. Data structure design goal. So how to get it? How to build that binary tree? All right, so now we want to use an array as the underlying data holder. Underlying, so array is used as the storage data structure, but we need to store a binary tree in the array. That's our design goal. Store a binary tree in the array. But the question, how can you store a binary tree? Right? How can you store a binary tree? The answer is very simple. If you can define parent-child relationship, then you can store a binary tree. Parent-child. What is the parent-child relationship? How to define it? If you can answer that question, then you make it. So, our next slide, we want to answer that question. How to define parent-child relationship in a simple way. Right. Yeah. So, most important, our next question. Parent-child relationship. Right. 8.2, binary tree structure in array. Something. All right. Then we only need to do one thing, define parent-child relationship. That's all we need to do here. Okay? All right. Let's do it. All right. Introduce the heap data structure. Heap data structure. Properties we need in this new data structure. Heap. What is a heap? Use an array as the underlying storage object. Okay? But we need to add more properties. Array is the starting point, but we need to add new properties. First, because this array, the elements in the array, can we arrange in a binary tree style, right? We arrange binary tree style. So let me give you a simple example. For example, when n equals 10, we have 10 elements in the array. Now, we want to arrange these 10 elements from top to bottom, from left to right, level by level, based on a binary tree. Okay? The first one at the root. Okay? 1, then go to one level lower, number 2, number 3. Okay? Another level lower, number 4, 5, 6, 7, 3 more, 8, 9, 10. Okay? So we arrange our array elements in this imaginary binary tree structure. Okay? Following the natural order. This is the natural order. From top to bottom, from left to right, level by level. Okay? In this way, usually we cannot get a complete binary tree, right? You know the complete binary tree. All levels must be full, right? All levels must be full. Here, the bottom level is not full. Okay? But we call it the near complete binary tree. only the bottom level may not be full. Other than the bottom level, all the other levels are full. If a binary structure has this property, we call it near complete binary. So our heap should have this kind of near complete binary structure. Like this one, yeah, exactly just like what I draw above. Yeah, only bottom level may not be filled. Yeah. Sufficient space for dynamic data. Then another property, sufficient space. How can you guarantee sufficient space for dynamic data? For dynamic data, data comes in, goes out. It's hard to predict how many total data items you need to store in your data structure, right? So the question, how do you maintain sufficient space for dynamic data? So this is another technical problem we need to solve, right? Yeah, technical problem. Can you imagine some smart way to make sure you have plenty of space to store dynamic data? But when data can grow, right? Data can grow. If the data keeps growing, sooner or later, your array cannot hold any new data item. The capacity is full, you have no room for a new data item, right? How do you solve the problem? How do you solve this technical problem when your array is full? We know when you declare an array, you have to fix the size, right? When you declare an array, you have to fix the array size. Okay? Yeah. You have to specify some concrete number for your array size. But that array, sooner or later, it will be filled completely. You have no room for a new data item. How do you solve this problem? You have to solve it. Okay? You have to solve it. So the solution is, can you create a new array with larger size and copy the data from the old array to the new array? Is that a solution? Create a new array with larger size and copy data from old array to new array. How about this solution? Feasible or bad? How do you feel about this solution? We just create a new array, double the size of the old array. New array, double the size of our old array. So we have a lot of room. But we need to copy the data from the old array to the new array. Then we can keep adding new data items. How about this solution? Feasible or not? Interesting or not? How do you feel? Yeah, so I will explain this. Yeah, yes, we can do it. Okay? Actually, people do it in this way. Okay? People do it. Okay? People do it in this way. But there is some technical details you need to consider. Next slide, I will show how to solve the problem. Right here. Certain relationship among nodes, parent-child relationship. We will see that formula. Okay, parent-child relationship. There is some simple formula. All right. Here, the question: how much space is sufficient? Nobody can predict, right? Yeah. We just make our decision on the fly. Okay. when you have a lot of data comes in, then we enlarge array. Yeah. So if your data keeps going away, we can shrink our array size, right? We don't need that huge array if the data all gone. Okay? We just shrink our array. Okay? We enlarge or shrink based on the needs. Okay? Yeah. Dynamic data. All right. How to know? Here, let me explain the idea I mentioned in the previous slide. How to make array space sufficient for dynamic data. Okay. All right. It is unknown, so we just keep monitoring our array capacity. Okay? If it's 90% full, we should be careful. Right? Already 90% full, only 10% space left. We should prepare a new array. Think about that. Prepare early, okay? Not, the last minute. Prepare 10% early, right? You have 10% space, room left. Now, create a new array, double the size, all right? All right. Idea, assign certain amount of space to an array initially. Initially, we don't worry, just assign certain, because we have some way to change the size. All right. Keep adding data and monitoring the size closely. Monitor the size. Okay. When a threshold is reached, you can set some threshold. Okay. 90% capacity threshold. Okay. A new array with a larger size is created. Okay. In Java, it uses double the size. Okay. Java. Early stage, early way, okay. Double the size. And copy the data to the new array. Now you have plenty of room, so you can keep adding, monitoring. Any problem in this method, if we do like the description here, can you imagine any special problem we may encounter for this kind of manipulation? Can you imagine? Some problem. There is some problem. Think about it. Well, your array is pretty big. Pretty big, the array. Okay? Millions of data items. Millions. How fast when you copy millions of data items from one array to another array? How fast it is? It will take quite some time, right? If it takes 5 seconds, for your users, is that significant? If you ask your user, wait 5 seconds, I copy the data. Is that very bad? It is very bad, right? So you don't want your users notice any significant delay. You don't want that happen. So you need to find a smart way to copy the data. So the user will not notice it. You make the data copy, but the user won't notice what happened behind the scene. You cannot see any delay. Is that good? Let me describe that idea. Data copy, smart trick behind the scene. Usually it is very expensive to copy a large. Expensive, that means it takes a lot of time, quite some time. Okay? So now, we don't want some bottleneck. So here, you can see that peak. Okay? Peak. So here, this curve represents the time used, response time. The peak. That means the data copy occurs here, so you use much more time. Okay? So your user, they need to wait much longer. Okay? And the peak place, they need to wait quite long. Okay? All right. Can you smooth this peak away? Can you flat this peak? Make, cut off the peak. Find a smart way to do it here. And let me describe. How do we chop this peak off? Yeah, I give you 1/2 of the idea before. Remember, when you monitor at some threshold, let's say 90% of the capacity, you already start preparation. Can you do it? You start preparation. You create a new array with larger size, and you can start copying already, right? Before it is full, you can start copying. But every time you do not copy too much data, copy part of it. How about that? Okay? Copy 100 data items. It won't take a lot of time, right? So the first time you copy 100 data items, okay? Another new data comes in, copy another 100. How about that? It won't take much time. Another new data item comes in, copy another 100. Okay? Every time you copy 100 until you copy all the older data to the newer. How about that? 100 data copy, it will be very fast. Okay? Let's say 1 millisecond. 1 millisecond, your users won't notice that. Okay? 1 millisecond, just right? So then you will flat that peak shape like this. Okay? Yeah. You will do so this part you will do a little more work because you need to copy 100 data items. You need a little more time. But your users won't notice that difference, right? The user won't notice that difference. So at the end, you copy all the data from old array to new array. How about that? This idea. So you solve that technical problem in a smart way. So your users won't complain. Won't complain. How about that? Okay? Yeah. So I remember I gave this kind of project before. Okay, simulation. Simulation, copy data. Okay, dynamic. Yeah. So probably in future I can assign a project like this. Okay? You need to you generate the data, you need to monitor the data, you need to copy, you know. All right, so let's move to next. So next important question. 8.3, heap hopping. I want to give you the parent-child relationship. Before we finish today, I want to give you that formula, parent-child relationship. All right. Relationship among heap nodes. Now, how to address the parent-child relationship? Now, we know we can store a binary tree, right? Yeah. You know, near complete binary tree. But most important thing that is missing at this point, definition of parent-child relationship. What's the definition? Here, it could be very simple. We don't want a very complicated definition. Okay? We want a simple definition. Here. All right. How to represent location of each node? Index. Given an index of an element, we know its location. Okay? 0, 1, 2, 3, 4. The location in our array. So that number we will use to reach its location immediately. Relationship between two nodes. How do we address relationship between two nodes? We just use their locations. How do we identify different nodes? We use their locations. Locations sufficient to identify different nodes. Here. Now, let us use a simple formula to define relationship between two indexes. Parent-child relationship. Now, the key step of this heap data structure. Look at this diagram. P refers to parent node. P colon I, its index is I. So we assume the index of the parent node is I, then we look at its left child, L, L colon, then the index for its left child, we use 2i. We want to make index location 2i as the left child of the P node. Right child, R colon 2i plus 1, the location with 2i plus 1, we want to use that node as the right child of the P node. That's our definition. That is our definition. And you will see this is the best way to define parent-child relation. Very simple, best way, very simple. And we can cover all the elements in an array in this way. All the elements we cover. Okay? If we use this way, there is no hole in the array. Okay? All locations will be covered. Okay? There is no hole in the array. Okay? Oh, actually there is one small hole, only one little hole. Okay? Only one. Can you see any special location is very special that we cannot put here? There is one special location. We cannot put here. It is dangerous if we put here.
Index 0.
Yes, index 0. Why index 0 is not good here? Think about it. You double the number. You double the 0, still 0, right? Yeah. Then the left child equals the parent node. That's not allowed. Child node and the parent node must be different. So we want to exclude location at 0 for our heap node. You cannot put a heap node at a 0 location. Okay? You have to exclude it. All right. After that, then it's pretty good. Then we will study the structure. All right. I still have 5 minutes left, so let me just say, we will go to deep study next time. But before let me finish this slide. Because in 5 minutes. So A of 0 is never used. Or in more precise way, A of 0 you cannot store the heap node, any heap node. You cannot. But you can store some other information, right? If you do not want to waste this storage location, you can store some other information, but do not store the heap node. Okay? All right. Relationship among heap nodes. 2 types of heaps. After we have this kind of definition, then we will study the heap. But study the heap, we want to use 2 different types. The first type we call the max heaps. Max heaps. The maximum number we put on top is max heaps. The opposite word, min heap. Minimum. Min heap. The minimum is on top of the binary tree. Just opposite. But we only need to study one of the 2, right? The other one, same way. So we don't need to spend our time twice on the same thing, right? Only once. So here we just study max. All right. What is the max heap property? Max heap property. Let me give you the max heap property. Okay. A of I, array value. A of I, that's the parent value, right? The parent value should be greater or equal to any of its child value. A of 2i is left child value. A of 2i plus 1 is right child value. If we have these two inequalities hold on every node in the scheme, everywhere in the scheme, then we have a max heap data structure. Max heap. That is our max heap data structure. Okay? So after that understanding, next time we will learn how to build a max heap. Okay? After we build a max heap, then how to do the heap sort. Then we will do the heap sort. Okay? All right? So that's for part A.